plus 5x to the power of, let's say, a half, that it divides everything by 2, like it factors out the 2 to the half, and you start with this term being 1. So you think of that factored out plus 5 over 2x. This is what it looks like. This is what you're doing. This is not something you need to remember really, but this is why it works so well. It works so.
Showing us why this happened.
Yeah, it works so well because when we do an expansion like this, the first term, like anytime you've this expansion, the first term is going to be 1. And then this one starts with a 0 power and increases from then on. And in certain particular cases, valid cases, or where the answers converge, it's called, this will actually give us an approximation for square roots and cube roots and that kind of thing. Okay, so we're going to look at an example now, but this is the theory behind it. This is why in the formula, when you see it, you see this a to the power of n taken out. Now a is the first term in the bracket here. So 2 is the first term here. We've taken that out, but we haven't applied the half to it. So that's where the n power. So if I want to completely remove this 2, I would do 2 to the power of a half. And now I've completely removed the 2 from the binomial part. Now I can just expand this binomial.
I don't get why it's over a.
Oh, here? Yeah, so originally this term, this is my binomial, the terms are 2 and 5. But when I actually go to expand it, this is the one that I'm going to expand, which looks more difficult, but it's actually easier to expand because this first term is 1. Now where did the 5 over 2 come from? It comes from 5 over these two, 5 over 2. So that's why this is b over a.
So why do you do 5 over 2?
You factor it out to get 1.
Yes, the theory behind it is to get this as 1. Now you don't have to remember that, but that's the theory behind it. So this is a 1.
Yeah,
And it's very easy to start a binomial with 1 because it's to the power of whatever.
Oh, yeah. Oh,
Yeah.
No, I get it.
And it means that every single term has only got 1 to the power of, so you can ignore this part of the binomial and focus on this part of the binomial, because 1 to the power 10, 1 to the power 9 is all just 1.
It
So-
was just 1/2.
Yes, in this case, yes. N is a half. So you'll see here will be a half. Here's going to be a half minus 1. So that's going to be minus 3 over 2, or no, minus a half, and then minus 3 over 2, and so on. So we'll do a more specific example, but that's where the theory comes from. Okay. So there was very specific, what was the interval for convergence, or where it's valid? How was that created again? Remember which one it is? The one you want to remember is the opposite way around to this. So a over b, x is going to sit between the positive and negative of that.
What is the absolute value?
It's negative a, and then
Wait, why do we do this with what are those things called again? No. Inequalities, because they're going to be the same.
This is just a way of saying between these two. So remember in our example from Tuesday, it was between minus 2 and 2. We wanted to say that mathematically. So it became 2 over 1, 2 over 1. So
How is that the same as bx over a?
oh yeah, so it was to solve. This comes from a solution of bx over a has to be less than 1, isn't it? So that comes from the it's like a convergence of a geometric sequence. Remember we did this 32, 16. This I can get an answer for of this series when I start to add these together because the ratio here is a half. And it's just similar, it has to be less than 1. If the ratio is any more than 1, so for instance, if I had a similar sequence but the ratio was 2, and I started adding them together, no, that's poor maths, multiply by, it is 32, 64, wasn't it? And so on. This answer is just tending towards infinity. This answer is getting smaller and smaller, so it's tending actually towards 64, and we've looked at that before.
How does that relate to
It's a similar process, because this, if we're adding up these terms, sometimes these fractions are going to get smaller and smaller and smaller, and That's what we want.
Okay.
That's what we want. Okay, let's look at an example. We'll use the formula. Yeah.
That formula is just for a singular term. You do that for each term.
That formula is the entire expansion. And you don't stop until the question tells you to stop. This is not like one where it's to the power of 10, it has exactly 11 terms. It's not as neat and tidy as that. It will go on forever until, it's like it's correcting the decimal places of, think about like that, of the square root. It's correcting it little by little. Whereas the major corrections happen at the start, and as time goes on, there's less and less of a correction.
Will the question tell you like stop after 5 terms?
Let's look at one. Okay, so this is pretty small, but we got, this is our 4 plus 5x, and it's to the power of 0.5, so they put it as a decimal this time. And up as far as the x term, it says. And find an approximation for the square root of 3. Okay, we'll come back to how we do that. So it wants to get up to the x term. So I want to expand this up, this term, this term, this term. How far do I need to go? I definitely need this one. Do I need this one? What's this one going to give?
Very close.
Remember, b is x. b contains x. So this is going to contain x squared. So I only actually want to do these two first ones. Just the first two. So it's not too bad. So let's do that expansion. What's my first thought here?
Make 4 1.
Factor out.
Yeah, so I'm factoring out. So this is the formula you'll have in the exam. So we'll use this. We know the principle behind it by factoring out, but we'll just follow it step by step here. So a here popped out in front. So this 4 here, I'm going to pop it out in front. And that's going to be to the power of a half. N. So if you want, throughout this expansion, a is going to be 4, b is going to be 5x, and n is going to be 0.5 throughout this expansion. So let's just plug in some numbers now. A was 4, n is to the power of a half. Maybe we prefer it like that. Let's stick to the decimals they give us. We'll maybe have to apply it slightly differently in a second because we know that square root. But anyway, 1 plus n is 0.5. b over a, 5x over 4. Remember, keep the x in there. And that's as much as we need.
So we need one more. We need the x squared, right?
It says up to the, as far as, I'm doing the first one, x term, and the second one's the x squared term. So I'm just doing part A. We might as well do part B as well while we're at it, and then we can look at part A and B separately. Let's just do the next term because we're on a roll here. What will be the next term? 0.5 times n minus 1. What's that? Negative 0.5 all over 2 factorial, which is 2 times 1. And b over a is 5x over 4. I've ran out of space, but 5x over 4, and that's squared. Okay, that's the first 3 terms. Let's tidy those terms up. What is this as a number? 2, yeah. So that becomes 2. 1 plus, what's this going to give? Yeah, it's way better to use a fraction, isn't it? But anyway, maybe it's 5x over 8, yeah? No? Yeah, 5, because that's 0, 0.5 can be a half, and then, yeah. What's this one going to be? Ooh. So that's a half times negative a half divided by 2. What's that much? That's negative 1 over 8. Negative 1 over 8 times 25x squared over 16. So what's 8 times 16? 128 maybe, yeah? Yeah, 128. It's actually, and this one's minus, is it?
Yeah, minus 25x.
Oh, you're right.
Minus 25x squared. Okay, so we've got the first 3 terms. Not too bad to just apply the formula, hopefully you see. You're given that. Once you find what a, b, and n are, it's just substitute it. Okay, how are we going to get an approximation for the square root of 3?
Can you just do 2 plus 5x over 4 minus 25x?
So the question, okay. So the approximation, they're trying to approximate root 3 using this. What relation has root 3? And leave your answer as a over b. So the first part of this question is up as far as the x term to find an approximation for the square root of 3 and leave your answer as a fraction, it's saying. Leave your answer as a fraction. What relationship does square root 3 have to this?
So if
So-
x is 1/5, yeah, if x is negative 1/5, then it would be square root.
All right, so how close? So yeah, if x is 1/5,
Negative 1/5.
Where'd you get that from?
yeah.
You can say it would be square root of 3. That bracket would have to be square root.
Yes, I want this to be this. So you can do a little equation here.
So you did 4 minus 1.
5x is minus 1 then. X is minus 1/5. So I can use x as minus 1/5 to get my approximation.
Why didn't we do that at the start?
Why did we do that at the start?
Yeah, why did, wait, what's
You could have done it as you went along. Yeah, you could have done it. Yeah. I just want to do the expansion first for A and B. So the expansion for A is up to here. The expansion from B is up to here. And if I don't even know, percentage error, we'll look at in a second. Okay, so if x is minus 1/5, so without a calculator, we're going to approximate root 3 using the binomial expansion. I'll leave that there. Okay, so the first two terms were 2, so this is part A, 1 plus 5x over 8. Okay, so now x is minus 1/5, so I can substitute in. I'm just taking the first two. It says for the first, just use up to x term. So I have 2 plus, maybe I'll sub in first, 2 plus 5 minus 1/5 over 8, yeah? So
2 times 7 over 8.
2 times, that's minus 1, isn't it? Minus 1/8, so 7, 2 times 7 over 8, you're right? Which gives what?
14 over 6.
4,
14 over 8.
maybe just a quick 7 over 4 here. 2 fits into that, 1's 2 fits into that, 4.
Wait, I don't get how
Hmm.
4